All right, so we are going to do example 2C. That's where we ended up yesterday. Example 2, part C. And let's draw a circle. So we found two things yesterday. We found the length of the arc and we found the angle of the arc. This time we're going to find the radius of the circle. Let's see what they give us. They give you a little angle right here. They don't tell you this angle, but they tell you another angle. All right, so we'll call that theta. So they call this angle, 330 degrees. So let's mark that. And so let's see. So they tell you this big old arc, if I can go all the way around, there we go. It's close enough. All right, so that red arc right there is 330 degrees, which it should be pretty easy to figure out what that angle theta is. What would that be? 30. Be 30, that's right. And they tell you the length of the arc is 4. Okay, from here, let's change colors. So from here to here is 4. Everybody got it? All right, so we have a formula, don't we? Remember what our formula was for this?
To find the radius?
Well, anytime you have the length of an arc, we had a formula for it.
Mm-hmm.
What was it?
Equals theta over 360 times the circumference.
Okay, length equals theta over 360 times the circumference. What is the circumference?
Pi r. 2 pi r.
2 pi r. Okay? Everybody got that? All right, so now let's just plug stuff in, see what we get. So here's the formula. Do we know the length? Do we know L? In this situation right here, do we know what L is? Yeah, what is it? It's 4. Good. Equals theta over 360. So what is our theta?
30.
It's 30 because the whole red one is 330. So this one right here will be 30 degrees because 360 minus 330. Okay? So what do we got? We got 30 over 360. And then 2 times pi times what?
R.
Times r. And we don't know r. That's what we're trying to find. Okay, that's the whole idea. Trying to find the radius. So now it's just a matter of doing some math and figuring it out. So what would you do here? I would get rid of the zeros, wouldn't you? I would. So that's going to be what? 3 goes into 3. One time, 3 goes into 36. How many times? 12 times. All right. So before we start moving anything over, I got a 12 on the bottom and a 2 on the top. Right? So 2 goes into 12, what? 6 times. So let's make this. It's kind of a mess. So let's clean it up a little bit. So 4 equals. What are we left with? What does all that canceling leave us with?
6 pi r.
Well, is it? Where's the 6? Right, it's 1 over 6. Okay, or you could look at it as pi r what? Over 6. That looks a little cleaner, doesn't it? With all that canceling stuff out. So what are we trying to do? What are we trying to solve for? Radius. So let's try to get r by itself. So what would I do here? Minus?
Times 6.
Yeah, there's nothing being added here. So let's multiply it by 6. So we'll multiply that side by 6. So that 6 will cancel. And we have to get rid of what? The pi. How do we get rid of the pi? Cross it out. Just cross it out. Divide. That's what I want to hear. Okay, you divide. So divide by pi. That'll cancel out now. Okay, you can't just cancel out the pi to begin with. Okay, you got to divide it by pi. And then what do you have to do over here? No. Whatever you do to one side, do the other side. So if I divided this side by pi, what do I have to do here? Divide that side by pi. So what does this basically come down to? R is equal to what? 24 what? Divided by pi. Now, you can put that into a calculator, and you get approximately, why did I put squiggles there? Why is it approximately? Why? Why is it going to be a bunch of decimals? Because of what? Because of the what? Because of the pi. Right, because of the pi. Now, you could just put it into a calculator. I don't know what I did. I just wrote down 24 divided by pi is approximately 7.6. So I don't know if I made that 3.14 or if I put it into a calculator and use the calculator version. I'd be interested to see. So let me get my calculator out. Let's see, 24 divided by 3.14. Yep, that's 7.6, and it might be the same thing. 24 divided by pi. Where's my pi button? There it is. Divided by pi equals, yeah, 7.6. It comes out the same thing. Okay, if you round it to one decimal place, it comes, either way, it comes out to 7.6. We didn't save. It's in feet, so always put your answer at whatever units you have.
Do we have to use it if the pi one or 10 would be worse?
Either way, in this situation, you still get 7.6. Okay, but I think I said before, let's just keep using 3.14 because then everybody's consistent, right? Then we don't have some people using the pi button and then some people using 3.14. If everybody uses 3.14, then everybody will get the same exact answer. Okay, so I think that's the best way to do it. And there really isn't a whole lot of reason to take it out any more than 2 decimal places anyway, right? 3.14, because you don't have too many things that can measure stuff that precise anyway. So that's usually why we do that. All right, that was pretty simple, wasn't it? All right, the key to that was to understand that formula right there. Okay, if you know that, so what did we do? We actually solved for we got 3 variables, right? We had 3 examples. One example, we found the length of the arc. One example, we found the angle. And the other example, one we just did, we found the radius. All right, so you should be able to solve for any of those 3 given that you know the other 2. Yes? All right, good. Let's move on. Do you remember we talked about sector and segment? I think we mentioned it briefly yesterday. So we're going to do something with that. I mean, you kind of figured we would, didn't you? Maybe, maybe not. Somebody did mention sector and segment yesterday. So yeah, somebody was thinking about it. So what we're going to do is not find the area of the sector and the area of the segment. We're going to find the length. And in this case, we're going to find the perimeter. Okay? And basically, don't give me like a formula, but what's basically the perimeter of any shape? The distance what? Right, the distance around the whole thing, okay? So the distance around the whole entire thing. So we are going to find the perimeter. I'll draw it here in a second, but I'll write down what they tell you we're finding. Of the sector X, U, Y, and the segment XY. All right, so let's draw it, put some letters in there so we know what's going on. And let's put it about right there. I'll put the center there. And then we're going to draw a couple radii. Draw one there. Draw one here. And let's connect from there to there. And let's put some letters in here. So this is X. Oh, no. Why is it doing this? What do I do to make it do that? If I double click that, yeah, see, look, if I try to do like this, see what it did? It's acting weird. Why does it do this? Well, let's do this. Looks like I got to restart it, but I'm going to keep recording. So if anybody's watching this, it's going to be really funky right now because something weird happens to my pen. I don't know if I click a button on here that makes it do that or what I'm doing. So let's see if I just get out of this. Yeah, it's just going to be blank right now, but just give me a second. So I didn't stop the recording. And let's just start this thing over again, see if it works. I don't need to write all that stuff in there, do I? Let's hit. Yeah, it didn't paste it on there, but that's okay. I can redo it. Let's see. Oh, I hate when stuff like that doesn't work. Let's see if it works now. So, yeah, all right, it works. Now, let's try the circle again. I'm not going to write all that stuff. You already know what we're trying to find. And let's draw from there to there. Let's draw from there to there. And then connect those two. And let's put some letters in here. Now let's see if it works. Yes, it works. Thank goodness. And this is U. And they tell you the radius, they tell you is 12. And they also tell you the central angle. It's 120 degrees. So we want to find the perimeter. I guess I will write this down. We want to find the perimeter of sector. What did I say? XUW? XY. Not W. There's no W's on there. All right, so sector XUY. What is that sector? So let's do this. Let's change colors. I'm not going to shade it in like perfectly at all by any stretch, but what is the sector? This. Agreed? All that in there. If I do all that right there, that's the sector. So keep that in mind. So what am I finding? Let's do this. I'm going from there to there. Yes? I'm going from there to there. And where else am I going? Around. That's right. So I'm going from there to there. Everybody got that? I guess we can just keep that there like that. That's fine. If that radius is 12, what's this XU? That's also 12. Let's change it back to white. All right. So really, to find the sector, to find that perimeter of the sector, really, it's not that big of a deal. It's 12 plus 12, that's 24, right? So we can do that with very, very minimal effort. What's the part that we really got to do some work? Find this arc. Find the arc. It's not really a semicircle. Semicircle is saved for what? Half of a circle. This is not half a circle. It's 120, right? But we just did it. We just finished doing one where we wrote down the formula. So what is the formula for the length of that arc right there? What is the length of the arc? Yep, theta over 360, 2 pi r. Okay. Now, we know theta, we know r, so this is about as straightforward as you can get with this problem. Would you agree? What's theta? 120 over 360 times 2 times pi times r. If you want to put it over 1, it's fine. That equals what? L. Everybody good so far? All right, watch. That cancels, that cancels. 12 into 36. 12 goes once, 36 what? 3. Good. Yes? All right. And I know the radius, don't I? Why did I put an R there? I know the radius, which is 12. So let's write it nice and neat, and then we'll put it into a calculator. So what's on top then? What's on top? Well, I'm multiplying everything together. There's a 1, but there's other stuff on top. This is on top as well. Give me a number. 24. That's what I'm looking for. It's just 2 times 12. That's all I'm trying to get you to do. Okay? Probably didn't explain it very well, but 2 times 12 is 24 times pi, and that's 8 pi over 3. No, that's fine. All right, so now, Timmy said it, 3 goes into 3 once, into 24, what? 8 times. So basically it's just what? 8 times pi. So, but I'm going to find a decimal, I think. No, actually they don't. They don't do a decimal until the very end. All right, so let's just leave it right there. Is that my answer, though? No. So let's not. Let's put it in a box instead. All right, so I'm going to hang on to that. So that's the distance from here to here. So really, what's the only thing else I have to do to find the perimeter? The perimeter equals what? That 8 pi plus 24. Yeah, just add them up in our heads, okay? This is 12, this is 12, that's 24. To tell you the truth, if you left it like that, I'd be perfectly fine. I would not have a problem with that. Unless I told you to give me like a decimal approximation or something like that. But if I don't say one way or the other, if all I do is just say find the perimeter, I'd be fine if you left it like that. But what if you really, really wanted to get a decimal number? Or what if I asked for a decimal approximation? You would just do what? Yeah, 8 times 3.14, and you get whatever that is, plus 24, and you get 49.1. And I put an equal sign. It wouldn't be wrong if you did, but I'm being picky. So I put a little squiggly equals 49.1. And that's in feet. So we put it in feet. So either one of these would be perfectly fine. Now I should have put feet right here. Sorry about that. And now we're good. So really, that wasn't that hard, was it? You just had to understand what it meant to be a sector, correct? And we studied that not too long ago. It was in the last chapter, I think, wasn't it? Yeah, I think it was the last chapter we did that. So there you go. So that's the sector. That piece of that pie is the sector, but we're finding the perimeter. We're not finding the area of it. We're just finding the perimeter. Okay, what's the other part of this say? Find the perimeter of the sector, and then find the perimeter of what? Of the segment. And what is the segment? So the segment is this part, and what other part? The bottom part? What do you mean the bottom part? XY, right. So I'm going to try to make this straight. Oh, I got a little nervous at the end there. All right. So that's what we're trying to find the perimeter of now. Whew, this one's a little tougher. I'm going to get rid of all of this just so I don't have to make another circle. Well, we already know XY, don't we? Or we already know the arc. Yes? So what was the arc? What was the arc XY? What was the distance from X to Y around that circle? It was 8 pi, right. So we already did it once. We don't have to do all that again, right? It's the same numbers. The numbers haven't changed, right? So I'll just keep it 8 pi. So really all we got to do is do what? Find the length of XY. Do you agree? So how in the world are we going to do that? Well, good question. Well, we don't have a right triangle, do we? Yeah, you got to have a right triangle to do Pythagorean theorem. What I'm going to do is I am going to redraw the triangle. Is that all right? Does that look close enough? Those two look the same? Yeah. Just so we don't have all that junk in there, okay? I'm going to push this over a little bit. Go ahead. Yes. All right. Nope, it's that time of year. I get it. I got them too. All right. I'll just make it a little bit bigger so we can work with it. Oops. Trying to group it. There we go. Now let's grab it. Come on. Come on. There we go. All right. So what do we know about this triangle? We know this is what? 120 degrees. We know that's 12, and we know that's 12. So really all we're trying to do is find this length right here. So how do we do that? That's the thing. Well, you had mentioned right triangle, didn't you? Or you mentioned Pythagorean theorem. Okay. Not necessarily going to do Pythagorean theorem, but watch this. These two are equal to each other, so tell me something about this angle and this angle right here. They're equal to each other, that's right. All right, so if this is 120, what do the two angles add up to be?
Oh, 9. Wait.
What do all three angles add up to be? 180. Take away 120. What's that? 60. So does that mean this one's 60 degrees? No, it means what? It means it's half of 60, right? Because they're both equal to each other and they add up to 60. So this would be what? 30 degrees. Now, do you remember? You may not. You remember what kind of a triangle? 30, 60, 90. But I don't see any 90 in here, do you? But we can make a 90. All right? And I could have a 60. In the same line, I'm going to draw one line to give me that. Watch. If I drew a perpendicular line to that longest side right there. Everybody see that? It's not drawn for you, but I could draw it. What did I just do? If this is an equilateral triangle and I draw a perpendicular, what kind of angle did I make? I made it a 90-degree angle. All right? Tristan, you're right. It split what in half? The triangle?
The angle.
What angle?
120.
The 120. Good.
That gets you 60.
Exactly. You got it. So look. So that whole thing was 120, but if I drew this perpendicular, we talked about this earlier. I'm not going to go through why and all that. But you got a 60 right here. Okay? All right, so I got a 30, 60, 90 triangle. Well, the 12, let's just take a look at this triangle right here. Okay? Forget this stuff over here. All right? It's the same thing. It's the same triangle. They're congruent triangles. So this is the, right in the middle, one of the hardest problems you're going to do. So let's pay attention. So this is your hypotenuse, correct? All right? This is what side? It's a 30, 60. We don't say little. What do we say? No. We don't say small. We don't say little. We don't say minor. Say short. Thank you. It's the short side. This is the short side. And this is the longer side. Okay, it's the longer leg. It's not medium. We said long and short. Okay, when we did these formulas, we used the words long and short. We're going to use the same words, okay? Let's recall what it was. Okay, they both deal with the short. Okay, so the long leg, let's do the hypotenuse first. The hypotenuse, do you remember this? Is equal to how much? 2 times the what?
Short.
The short leg. Okay, and then the long leg, here's the one. Very good. The square root of 3 times the short leg. Everybody with me on that? So, let me see what we're going to do. Okay. So you could find this side and this side now. Let's do it. Let's find them both, just for fun. Okay? Let's find this one right here. Now, I know the what? Well, I know what? What is the side? The hypotenuse. I know the hypotenuse is 12, so what's the short side? It's 6. That's right. Because if I double the short side, it equals the hypotenuse. Correct? What about this side? Now that I know the short side, it's kind of easy to find the longer side. What do I do to it? It's just 6, what? Times the square root of 3. Everybody with me? So it's nothing new, right? We've done this before, but it's been a while. So I don't expect you to remember every little thing we've ever done, but it's coming back to you though, isn't it? Yeah? Okay. So now again, what was our goal? Our goal was to find the length from here to here, correct? All right, what were the letters? We'll call that X. We'll call this what? Y. I shouldn't have put a little cross thing here. But anyway, from X to Y, that was what we were trying to find. Well, we found this. That's 6 times the square root of 3. So what is it from X? We'll call this M. What is it from X to M? What is it from X to M? It's 6 times the square root of 3. You were just saying what you thought I was going to ask, but that's not what I asked. Now, Tim, you could tell me, what is XY? What is that whole length right there? It's 12 square root of 3. That's right. Okay? So that's 12 square root of 3. So, we're almost done. What is the perimeter of this red segment, right? So you only got 2 things, right? You got the arc and you got this straight line right here. So let's do it doesn't matter. Let's do the square root one first. So what do you get? 12 square root of 3 plus what? 8 pi. And it's in feet, so we put feet. And you could just leave your answer just like that. I would be perfectly fine if you left your answer like that. Okay? We didn't need a calculator one time for this, did we? You know, all this crazy stuff. But what if I asked you, and I don't think I do, but what if I asked you to put this into decimal, into a, to round it to like the nearest, what did I round it to? The nearest tenth. What if I said, round your answer to the nearest tenth? Would you write your answer like this? No, this is not rounded to the nearest tenth. This is an exact answer. Everybody got it? If I say, give me an exact answer, you would have to write it like this, right here. Okay? But what if I said round it to the nearest tenth? What would you do with this stuff? Put it where? In a calculator, that's right. So I'm not going to do that. You can do that. Check to see if you know how to do that. So I would put it into a calculator, and if I round it to one decimal place, I don't know what it comes out to be, but it'll round to 0.9, and that's in feet, so we put feet, and then that would be the approximation for the perimeter. And that's how you do it. What do you think? We good? Yeah. All right, that's the hardest thing we're going to do today. We're going to talk about 2 more theorems real quick. Pretty simple. So I'm going to copy and paste that. So what's true about these 2 circles if I copied and pasted it? Equal, congruent, right? We say, when we use shapes, we say congruent, okay? The geometry book, actually, even when you do line segments and things like that, they say congruent. But I usually save like line segments and angles and just say that they're equal to each other. But definitely when you have shapes, we would say that they are congruent to each other. All right, so we started off with congruent circles. I'm going to put the center in both of these right there. All right, and let's do this. I'm going to put an angle right here and right here. Not anything special about those angles. Let's do this. I'm going to copy that and paste it, and I'm going to rotate it. Rotate it anywhere like that. All right, and then grab it and... So did I change the length of the radius at all? No, I copied and pasted it, so it's the same exact radius. Did I change the angle to it? No, kept the same exact angle because I copied and pasted it. Everybody with me? All right, so that means I got 2 congruent circles. If I have 2 congruent circles, that's a what kind of an angle?
Small.
Where is its vertex? Its vertex is where? Okay, so it's a central angle, right? So that's a central angle, and this is a central angle. Okay, so here's the thing. Everybody listening? It says, in congruent circles, I got congruent circles. Or you could do this in one big circle if you wanted to. I just didn't do it, okay? I could do one big circle, right? Have an angle come in this way, have an angle come in this way. You with me? All right? And if those 2 angles are congruent to each other, so those 2 angles right there are congruent to each other, what do you think might be true about the arcs? ABC and then D, E, F. Okay? So what do I know about arc AB and arc DE? They would be equal to each other, okay? Because it's not just because this angle is equal to this angle, all right? It's because the circles are congruent to each other, the angles are equal, right? That means the what? The arcs are equal to each other. So I can put a little tick mark, okay, for the arc if I wanted to. Actually, nah, that really means that the length of the arc is the same, which would actually be true, but the arcs themselves are equal to each other. So we can say that arc AB is equal or congruent to arc what? DE. Does that make sense? It's kind of self-explanatory. I mean, if I just showed that to you, I bet you every single person in here would say, oh yeah, those 2 arcs would be the same. They'd be equal to each other. Wouldn't you agree? Because if they both had the same central angle, yeah, they would. Everybody got it? Okay. So that was pretty easy. Not that big of a deal. And we got another one that's kind of the same. Tell you what, I'll keep those two circles there. I'm going to get... now let's do this. If only if they're I misspelled that. If they intercept congruent arcs. The chords are the same. Okay, so here's this. Watch. If I connect from A to B and then I connect from D to E. And what if I told you right at the beginning, what if it could go either way? So watch. If I told you that arc AB and arc DE were equal to each other, then, watch. Now I stuck something different in here than on that first theorem. What did I put in here? I connected A to B and D to E. So look at the length of AB and look at the length of DE. If those circles are congruent, and this arc AB is exactly the same as this arc DE, if they're congruent to each other or equal to each other, what do you think is true about the length of AB and the length of DE? They're equal to each other. So the length of AB is equal to the length of DE. Notice I didn't put anything over top of it. What does that mean if I don't put anything over top of it? It means the length of, that's right, the length of AB is equal to DE. It could go the other way too. Watch. You could say if the length of AB, right, that chord, so if this length was equal to the length of DE, what do you think you could say about the two arcs? What do you think about arc AB and arc DE? Then they're equal to each other. So I'm going to put an arc is equal to arc DE. Everybody see that? And again, it's kind of self-explanatory. You could probably have just looked at that and said, yeah, that's probably true. Right? So if I have the same circles, congruent circles, and I got the same arc, right, the same angle, creating the same arc, if I connected the two, and I connected the two, those two line segments are going to be exactly the same. Wouldn't that make sense? I mean, there's no reason why this would be bigger, would it? The only reason it would be bigger if this angle was a little bit bigger. And then those arcs wouldn't be equal to each other, would they? All right? But if they're equal to each other, then this segment and this segment would be equal to each other as well. And that's it. We finally finished 8-3. It took us 2 days, but that's okay. All right, so I think yesterday I didn't officially give you homework, did I? I said do as much as you can, right? So now this is official. So it's what, 2 to 16? Did anybody actually do some of the homework last night? Okay, so you don't have near as much to do then tonight. So it's 2 to 16. You should be able to do them all. And it's section 8-3.
I think it was 2 to 12.
Nope, 16. On my lesson plan, it says 16. It's page 365. Page 365. So there you go. Here, I'll give you a quick sneak preview of what's next week. You want to see? Bet you can't wait, can you? So watch this. We talked about this angle, and we talked about it today. And we've mentioned the name of it today. What do I call that angle right there? It's the central angle, isn't it? Okay. What we're going to talk about on Monday is this. Everybody watching? We are going to take an angle not from the center, but from a point on the circle. So let's take a look at this. See that angle theta? And this one, just call it little angle A, call it alpha. All right, it's not really what an alpha kind of looks like that. It's kind of weird. I can't draw it. Okay, let's say we have this angle right here. Is this angle look the same as that angle?
No.
But there is a relationship though. All right, so watch this. What if that arc right there was 80 degrees? What's this angle in here? That's 80 degrees. What's a wild guess? There's no reason for you to know this, but just what's a guess of what this angle is equal to? Well, watch. What'd you say? 40? Exactly right. And that's exactly what it is. That would be 40 degrees. Do you see the difference between the two angles? Look, the vertex of this angle is in the center of the circle. The vertex of this angle is where? On the circle itself. Look, I could draw what's really cool. I could pick any point on the circle. Watch. If I went to there and then I went to there, what's this angle right here? This is also 40. I could keep doing that forever, couldn't I? All right. So look, this angle and this angle would be equal to each other because they cut off the same exact arc. You see it? So that's what we're going to be talking about on Monday. Isn't that exciting? I bet you can't wait. I'm kidding. I know it's not that exciting, but it's still kind of interesting to see all this stuff and how it happens. I mean, what's cool to me, I thought we were out at 20 up, but we got a lot more time. But that's all right. I'll shut up after this. What's really cool to me about geometry and about algebra too, but algebra also, but I think that when you see stuff like this, it's not like people made that happen. You hear what I'm saying? Right? It's not like somebody said, I think I'm going to manipulate this shape so that this and this are equal to each other. They don't. It just happens. But does it just happen? Do you think? You think it just happens? No. I think it was designed to happen that way, don't you? All right? And who do you think did the designing? Right, that's right. God did that. Okay, absolutely. All right? So God designed it like this. Okay, a lot of the things, like the in my other class, it's been a while since you guys have done this, but do you remember you had a rectangle and then you took the diagonals to the rectangle? Did people actually make that happen? That the diagonals are equal to each other? Because they are. Those two lines are exactly the same. All right? Did people make that happen? No, it wasn't somebody's idea. I'm like, you know what? I think I'm going to make something where those two lines are going to be equal. No, it happens. It happens in, I hate to say this, it happens in nature. But a lot of people say nature when they really should be saying what? God, right, did this. He's the one that did this in nature. He's the one that made nature. All right, so this actually, I think it's kind of interesting. And that's what I like about geometry is that we're discovering what God put out there. That's what's cool about this. We didn't just make it up ourselves. Like calculus and algebra and stuff, man made that stuff up, right? But this geometry thing, all right, with all the shapes and all these different things, God designed it in a very special way, and all we did, not me personally, but people before us, they discovered it, right? And they, we just have an understanding of it. That's why I think geometry is so cool, because it's a design. It's been designed before we were ever around. All we're doing is just looking at it and saying, wow, look at that. That's so cool, right? It may not be that cool that these two angles are exactly the same, right? They cut off the same arc, blah, blah, blah. But as you get older and you start having more appreciation for stuff, I think it's kind of interesting to see all that happening. So just keep that in mind when you're doing geometry, all right? It's I think it's pretty cool. And it's stuff like in a public school, I wouldn't be able to say that kind of thing. I would say, well, in nature, it happens in nature. I would say that, because I wouldn't be able to say God was the designer. Some schools, some principals would probably be mad even if I said that there was a designer. Because what does the world believe? The world believes what? Yeah, the Big Bang Theory, that it just happened. It was random, right? But it wasn't random. If you look at all the evidence in this world, there's no way in the world that the stuff that we have naturally in this world was a random event. It's not random, okay? It was designed. We had a designer. I heard somebody say, think of the most complicated thing, like a car. A car is like so incredibly complicated. If you just took a bunch of rocks, okay, and just sat there and you waited 1,000,000 years, 2,000,000 years, 1,000,000,000 years, 1,000,000,000,000 years, would it ever come together to be a working car? No. There has to be a what? A designer, right? There's got to be somebody that designed it and say, this is what we're going to do. We're going to cut this way. We're going to do this. We're going to put it together. We're going to make a car so you can sit in, you can go down the road, right? There's no way, no matter how much time is given, there's nobody to convince me that enough time would go by for something like that to happen. Would you agree? And that's the way with the universe. Okay, there's no way in the world, no matter how much time went by, that the universe is the way it is because of time and randomness. There has to be a designer. And that's what I think is cool about the school, is we can come and talk about that, and we don't have any repercussions. In fact, we're actually encouraged to talk about it, right? We're not just not discouraged. We are encouraged to talk about it. Maybe in Caravel, they wouldn't have a problem with a teacher saying stuff like that. But if you went to William Penn or Middletown or Appo or something like that, or whatever public school you want to go to, they probably would not be allowed to say that kind of stuff. And I think it's cool that we can say it in here. So anyway, I don't know how I started thinking about that. I just did. I don't talk about that kind of stuff too much in here once in a while. I just thought it fit pretty well right here. All right, enough of that. I'll be quiet. You got a few minutes. You can just chill and wait for the bell, okay?